Again to Let's Talk Chemistry with Pastor Dan. We're looking today at molecular geometries and bonding geometries. Now, these have to do with covalent bonding, the way they're shaped. In order to understand this, something we call Vesper valence shell electron pair repulsion theory, and that has to do with hybridization and polarity and all those kinds of fun stuff. Now, let's define each of these. Molecular geometry is defined as the shape of a covalent molecule based on the number of bond sites. Now remember, bond sites are bonds as well as unbound electron pairs. So however many around the center, that's what we're looking at. And bonding geometry is defined as the shape of a covalent molecule based on the number of bond sites, so like the geometry and the number of bonds. We look at both of those things in order to come up with a bonding geometry. Now, we have definite structure here. The first one here looks linear. So we have two bond sites and two bonds. It's linear. It looks something like this. All right? Or if you want to look at, take a little marshmallows for my students, the atom in the center, one on each end, straight across. And I'm using two toothpicks to represent a double bond here. And that would be linear. Now let's do, if it's three bond sites and three bonds. Well, it's three bond sites and three bonds. We call trigonal planar because if we look at it here, this is the structure. It's a triangle and it's all in the same plane. And whenever the number of bond sites and bonds are the same, bonding geometry is also trigonal planar. So there we go. And here's what it looks like for there. So you see the flat layer, that's a plane. And you can see the triangle, that's trigonal planar. All right, now we get interesting. This is the one that's the toughest people to draw. Oh, no, it's not yet. I'm sorry, I got ahead of myself. So three bond sites, two bonds, trigonal planar. But now we take this one and we lose one. So we don't have a straight line anymore. Instead, the line is bent. So the bonding geometry is bent. And there's the structure there. We see a line, the triangle with one point missing because it's an electron pair pushing those down. There we go. That's bent. All right. Now let's go fourth one. This is the one that's a little bit harder to draw because if you try to visualize, most people try to make a cross, and I'm cool with crosses. You should know that, but not here because crosses are only at 90 degrees. We want to get them as far apart as possible. So get them as far apart as possible. It's about 109.5 degrees. We call that tetrahedral. Think of the game where you drop those four boxes, and that's called Tetris. Well, four sides, Tetris, tetrahedral. Four bond sites, four bonds. Bonding geometry is also tetrahedral. And here's the structure. Now, you can see what I have here so that whenever you flip it over, it should always look the same. That's the best way to make it. If you flip it over and it looks different, something's not right. Alrighty. So now, four bond sites, three bonds. Again, molecular geometry is still tetrahedral. But now we're going to lose one. So if we lose one off the top, we've got a triangle here, but it's not flat now. It's a pyramid. So the bonding geometry is trigonal pyramidal, not pyramidal, pyramidal. Four bond sites, two bonds. Molecular geometry is still tetrahedral. Bonding geometry, now we have our tetrahedral. Trigonal bipyramidal, we lose one more. We're back both again to a structure where the line is not straight, but rather it is bent. So the structure looks like that. There we go. Alrighty. So let's get to five bond sites. Now we're getting into superoctets, larger than five. All right, so let's go five bond sites. Five bonds, get them as far apart as possible. The structure here is trigonal bipyramidal. All right, so let's find it here. Here's our structure. We have a triangle on the x-axis, and we've got a line up and a one going down. So we have a pyramid here, a triangle pyramid here, and a triangle pyramid here. So that's why it's trigonal bipyramidal. And the number of bond sites and bonds are the same. So the bonding geometry will be the same, just as we've been doing. And there's the structure. You see the triangle right there, one top, one bottom. All right. Now, if we get to five bond sites and four bonds, molecular geometry again is trigonal planar. In fact, if we want to, we can just run these all the way down. Molecular geometry, whenever we have five bond sites, is always going to be trigonal bipyramidal. But if we go to 4 bond sites, now where are they farthest apart? Well, this is 90 degrees. This is 120. So 120 is the most. So I'm going to lose one of these. Now, if you look at this, what shape from your childhood that you played on does that look like? Hopefully you remember a seesaw. Now, when you go to college, you might run into professors that don't like seesaw because it seems too juvenile for them. I've heard it called irregular tetrahedral. I've heard it called bent cross. But I like seesaw. We're going to use seesaw. And the structure right here, you can see there's the end, there's the fulcrum, there's our teeter-totter, our lever. That's a seesaw. All right, 5 bond sites, 3 bonds. All righty, so we got our seesaw. We want to lose the ones that are farther apart. Again, the 120s are farther apart. So what letter is that going to be? Right there, hopefully you see. That's a T shape. That's the name of the bonding geometry because that's what it looks like. Okay, there's T shape. All right, 5 bonds, 5 bond sites, 2 bonds. So if we're at T shape, which one is farthest apart from the other one? This one on the bottom, so we lose that one as well. Now we're back to a straight line again. So bonding geometry would be linear. All righty, there we go. Okay, last set then. If we get to 6 bond sites. Now, 6 bond sites, get them as far apart as possible. Where's my 6 bond sites at? I brought it over here. I know I did. 2, 2, 2, 2. Oh, did one of those come off? They did. All righty. All right, hold on a second. I just got to pull one out of there. Put it inside of there. There we go. Okay, so the structure, they're all at 90 degrees. It looks something like a jack. Is what I was at if you played the game Jacks. All right, now if we made each of these a plane, we'd have 4 on top, 4 on the bottom, so that's 8. So molecular geometry is octahedral. Whenever bond sites and bonds are the same, the bonding geometry is octahedral. And again, whenever we have number bond sites, molecular geometry, you can go straight down this line. That's octahedral. That's octahedral. That's octahedral. And that's octahedral. And the structure, right there, you can see that jack, everything at 90 degrees. That's octahedral. All right, now, 5 bond sites. We're going to lose that one I just plugged down there. So now we have a square there. Well, that's not quite perfect, but that's my square. And then I've got a pyramid on top. So the bonding geometry is going to be called square pyramidal. Not pyramidal again, pyramidal. And here's what the structure looks like. Remember that bottom's off of that jack. All right. 5 bond sites, 4 bonds. Now, again, we want to come as far as possible. So one on top is one we're going to get rid of. So now we're back in the same plane again. And if you look at that, that is or should be close to a square, so the bonding geometry is square planar. All right, right there. All right, now, if we're at our square planar and we want to lose one more, it doesn't matter which one we have. That should look familiar. Yep, that's right. We're back to T shape. So 5 bond sites, 3 bonds, bonding geometry is T shape. All right, and then lastly, if we have our T shape, we're going to lose it off the bottom. So again, straight back to a straight line. Linear. Okay, so those are the shapes of covalent molecules. We will practice those tomorrow and go through them. Hopefully this wasn't too bad. Take care. God bless. Goodbye. Oh, let's do some practicing. Get ahead of myself here. So draw these structures. Let's do the number 4 first. If we do the structure here, the first one rather, we have carbon dioxide. There are 2 bond sites. There are 2 bonds. So molecular geometry is linear. Bonding geometry is linear. All right, let's do the 4th one. So we have 5 bond sites, and we have 4 bonds. Molecular geometry is trigonal bipyramidal, and with 4, remember, we're going back to that funny one that some college professors don't like, seesaw. All right, let's do the second one there. BCl3. Remember, boron's a moron. It's happy with 6. We don't need to go any farther. So there's boron trichloride. So therefore, there are 3 bond sites and 3 bonds. All right, structure looks like molecular geometry, trigonoplanar, all in the same plane. And because molecular geometry and bonding geometry, bond sites and bonds are the same, bonding geometry is also trigonoplanar. All right, last one here then. H2SE. Structure looks like this. Now we have 1, 2, and then 2 unbonded electron pairs. So that's 4 bond sites. But we only have 2 bonds. So therefore the molecular geometry, 4, remember the boxes that drop? Tetris, tetrahedral. And it's not a straight line, rather it's bent for the bonding geometry. All right, now we're going to practice these. Stop the video, do the Lewis structures for these first, and then identify the number, the molecular geometry and bonding geometry for each. Okay, pause it. All right, here we go. 5 bond sites, 4 bonds, 4 bond sites, 3 bonds, tetrahedral, trigonal, pyramidal. Okay, so next one we have 6 bond sites, 4 bonds, octahedral, square planar. All right, next we have 6 bond sites and 3 bonds, octahedral, T-shape, and the last one, oh yeah, you love that one, didn't you? Because you have those resonance structures, have to have the brackets around them. There are 3 bond sites, 3 bonds, trigonoplanar, trigonoplanar. All right, now we're done. Take care, God bless, and have a good day.